All right, so today we're going to continue looking at roots. We're going to investigate a method called the bisection method. And so, so far, remember what we've done. Remember what we've done so far is, well, first pull your bisection class example starter. May not say starter on it, but you'll need the incremental search starter code. And for those of you that have finished your incremental search, those modifications, you don't need the starter code. You can just use incremental search. But if you run that, we'll pull up the function that we've been using before, which is this y equals sine 10x plus cosine 3x. Okay, so we'll just stick with this function. In fact, the practice problems for today are going to be using the same practice problems that you've done before. Okay, so we're just going to keep looking for roots using these types of functions. Okay, and so just as a recap, the first thing we did is that when looking for roots of the zeros in this equation, we just zoomed in, right? We just did a graphical method. We are going to, take our magnifying glass and come in here and say, all right, it's going to cross 0 in between 4.22 and 4.24, and it's going to cross 0 between 4.28 and 4.3. Okay, 4.26 and 4.3. And so from that, you can zoom in, and if you zoom in enough times, then you'll be able to hit the precision that you want. Okay, and that's also provided that you have enough data points in your function itself. Okay, and we said that's a great method to use if you just want to find maybe 1 or 2 roots, but anytime you need to look for a series of roots, so restoring our view here, if we want to look for a series of roots, and in this particular function, there are 9 roots that we're looking at in this gap between 3 and 6. And so, so last time we developed a method to come up with what are called brackets. And so if you recall, a bracket is any interval which contains at least 1 root. Okay, and specifically based on the method that we used, which was comparing the sign change within a bracket. So if there's a root, if there's a single root, then it's going to be positive on the upper side of the interval, and then it's going to be negative on the lower side of the interval, as we're seeing here. And so we could find 1 root, or another option would be here, we would get the same, we would get a positive bracket, or we would test positive for a bracket, and this would have 3 roots, because that we have a sign change. It's positive on the lower bound and it's negative on the upper bound. So the sign change is in place, but it contains 1, 2, 3 roots. Okay, and so we talked about changing the interval size, or the number of intervals, per on your domain, to be able to do a better job at locating the roots. And so when running this code, you get that we found 9 brackets, and on each of these you have a lower bound and an upper bound, and these are all saved in this particular code in a variable called brackets, which is a 9x2. And the next step would be to employ the F0 command, right, which is the built-in, we're just going to call it the black box method that MATLAB has here, that we're decomposing. So we're just trying to take out what we would use in F0. And using F0, we would give it our function. That would be our test function. So we're using our function handle to send it the function. And then we would give it something like brackets. And I want my 3rd row, both columns, which is going to give me, let's see here, my 3rd row will be the root between 3.72 and 3.75. And so if let me put in the right syntax there. And so if I run this again, the answer it gives me is 3.75. Let me change my formatting on that as well. So let's do format short G, because I think we need some more decimal places than that. There we go, 3.7457. And so if we zoom in that region, then we should see that indeed this root lies at 3.7457. Okay, so that's what we've done up until this point. we figured out a way to isolate a region around the root, and then we're still going to another function to actually go find the root. So today we're gonna take one more step, and we're gonna say, all right, I found out what my bracket is, and after locating the bracket, which with this bracket it was 3.72 to 3.75. I'll do my best to zoom in on 3.72 to 3.75. Let's see here. At 3. There we go. So there's our bracket, roughly. 3.72 to 3.75. Now, how do we actually go get that point itself? Now, there's two different ways to do this. Two different styles of ways to do it. One is continuing with our bracketing methods, and that's what we're going to do today. And then next time, we're going to start doing what are called fixed point iterations or open methods. Okay, but today let's stick with our brackets. And so, so considering this, all right, let's draw an example of where we have a bracket. So I have some function of x, and then there's our x-axis. And say in here, I have a bracket that we've defined in some way. Now, we can visually inspect this, and we can see that right here, I mean, this is our root. And we've already said that we're looking for where our sign changes. Okay, so we've got a point here where our sign of our function, f of x, is greater than 0. And we have a point here where f of x is less than 0. Okay, so that was our first step of determining where the bracket was located. But now you can see here that our root, okay, is somewhere in between the brackets. Okay? Now, one way that we could do this, if we're now considering that these are all numerical methods, so they're all algorithms that give us approximations, right? So one way that we could do this is we can certainly say, all right, all I want to do is find out where the middle of the bracket is. Okay. And then that midpoint, you know, this can be my approximate root. Okay, and that's a fair assumption, okay, because we're using approximate methods, and when using approximate methods, we never get it exactly right. Okay, or we can expect that we're not going to get it exactly right all the time. Let me rephrase that. Okay, and so if that's the case, that means we do have an error, okay, in our approximate root, because if we then plug in this value of x and we calculate our f of x, okay, then our error and this is going to be a true value error. Okay, our true error will be this amount. Okay, does that make sense? Give me a thumbs up if you're following me so far. Okay, great. All right, so now we're kind of asking the question now, how can we make that error less? And so what we're going to be doing, this is a nice graphical, there's a good graphical explanation of this, and a graphical explanation of this method. And what we're going to be doing is something that's called bisection, okay, or bisecting the bracket. So here we have our domain, our new domain that we're working in essentially is just in this bracket. And so for this bracket, I have an x lower and I have an x upper. And so if I bisect the bracket, so when you hear bi, what do you think about when you hear the prefix bi? 2. Yeah, it should be 2, right? You guys write bicycles, okay? And so if you're going to bisect something, okay, or bifurcation, that's another really interesting nonlinear phenomenon. Okay, but this bi is all over the place. So if we're going to bisect something, we're going to cut it into two parts. In this bisection, we're going to cut it into two halves. And so that means that I'll change my color here. Let's find, let's use blue for this. All right, so that means that I'm now going to cut this into two new intervals, okay, that are halfway across. And I'm going to apply then, I'm going to choose which interval satisfies the sign change criterion that we used before. So by now having an interval on the left, a lower interval, and an upper interval, to apply the sign change criterion, okay, here f of x is greater than 0 on this lower part, and here f of x evaluated here is going to be less than 0. So the sign changes from this point to this point. Make this a little smaller. But the sign change doesn't occur from this midpoint to here. Okay, so what we're going to do now is we're going to say, well, here's my new interval. And instead of what we had before was there's my lower bound and there's my upper bound, I'm now going to take this midpoint, I'll call it xm, at this point here, and that's now going to become my upper bound. Okay. Does that make sense? So now I have an x upper, and I have a new bracket. And so with this new bracket, we're ready to then bisect it again. Okay, I'll put a construction line right in the middle. And we're going to be choosing, do I want this side or do I want this side as my new interval? So we're going to make that choice based on the fact that here and here, okay, f of x is greater than 0, and then at this point, f of x is less than 0. And so that means my new interval is now here. Okay, so now this is my new bracket. So essentially we're changing the bracket over and over and over. And ultimately we're wanting to get to a point where we're then going to choose our x value here where the root is. So as we continue doing this, okay, we have our x upper, here's our x lower. This was our new x mid, or xm. And now our xm is going to become our new x lower. Now there's our x upper, right? So then our next step is to cut this in half again. Right, here's our x mid. And then we're going to choose which one of these we have greater than 0, less than 0. So now here's our new interval. All right, so there's our x lower, there's our x upper. Okay, and we just do this over and over and over. And hopefully you can see we've started out with this big bracket, and our bracket's getting smaller and smaller and smaller. Okay, until by the very end, there's going to be some point in which we can say, all right, there's my x mid or my midpoint. And then using that midpoint, that's now, we can call that our root. Okay. All right, did you follow me through that? Give me a thumbs up if you got it. Okay. All right, so most of you have followed that, so that's great. And so the process that we're going through here is that we've got a bracket, and then we find a midpoint, okay? We can say that's our approximate root. We're going to evaluate which interval we want to keep, and then we'll replace either the lower bound or the upper bound with that midpoint, okay? Then find out which interval we want to keep, calculate a midpoint, find out our left interval, right interval, okay? Then replace the lower bound or the upper bound with the midpoint. And that's how we're going to work our way into finding out what that root is, okay? So I want to work through an example by hand. And in the example being one that we're just going to grab from our function that we have here. So we've spent most of our time, as we've been talking about this this trigonometric function, talking about either this root here or this root here. Okay, our root here on the left it's like 4.229. And so let's take this. This is our fourth root. Okay, as we're working through our roots or our brackets. So between 4.20 and 4.23. That's our root that we're working with. And so let's use the bisection. And this is on our function, f of x is equal to sine of 10x plus cosine of 3x. And then let's find the root between.
We cannot see your iPad screen.
Oh, thanks. Appreciate it. Okay, can you see it now? Okay, so we want to find the root between 4.20 and 4.23. Okay, and this is the bracket that we've already identified. So this is our fourth bracket using the interval search. And so to do that, let's make a table. And on the left side, we have the iteration that we're going to use. Since this is an iterative method, right? We're closing that bracket. And on this, I want to have a lower bound, okay, and then an upper bound. And then a midpoint. And this midpoint, I'm also going to call that our root approximation. Okay, so always be thinking the middle between the lower bound and upper bound as we're closing them is going to be our root, our new approximation. And then at the end, we want to evaluate at f is equal, at our function at x is equal to the midpoint. All right, and so this gives us our comparison. We should see this get closer and closer and closer to 0 if this works. So on our first iteration, so iteration number 1, okay, our lower bound, 4.20, and our upper bound is 4.23. Okay. Now, we've already seen here that on our lower bound, 4.20, our function of x is greater than 0. Okay, that's our positive. We get a positive value. And then on our upper bound, because this is a legitimate bracket, our function evaluated at the upper bound is less than 0. That's our negative value. And so our goal here is to keep these that way, right? So that the one on the left-hand side, oh, sorry about that, guys. Can't get everything on here. Okay, so what I was saying is that f of x for our lower bound is less than 0. F of x for our upper bound, I'm sorry, f of x for our lower bound is greater than 0, it's positive. F of x at our upper bound is less than 0, it's negative. And we want that to be the case throughout the entire process that we're going through. Okay, and that's what keeps that bracket, okay, our new brackets around the root. And so, and then our midpoint, of course, we want that to eventually be 0 when we evaluate it. So when we evaluate our lower bound and upper bound, let's calculate our midpoint because we know we need to get our midpoint. And to do that, the equation I want you to use is our lower bound plus the upper bound minus the lower bound divided by 2. So 4.20 plus 4.23 minus 4.20 divided by 2. And that gives us an upper bound of 4.215. And so 4.215 being our midpoint, let's calculate then, we'll insert 4.215 into our equation. And then we get 0.030907. Okay, I took it out to a lot of decimal places here. Okay, so now we can see here that this is pretty darn close, okay, to 0. And now it's up to us to say, what type of tolerance are we satisfied with, right? So this is where our error criteria come in. And let's set an error criteria. Let's say that our absolute true error, our true absolute error, we want this to be less than or equal to 0.001. And if that's the case, then we haven't hit that yet because we're at 0.03. Okay, our function here, and does that make sense? This is why our function is actually equal to our error if we take the absolute value of this. All right, so for our second iteration, it's iteration number 1. For our second iteration, we have our lower bound and our upper bound, and we've got our midpoint. And so following along with this idea here, where we start with a larger bracket, and then we're going to change our midpoint to be our upper bound or our lower bound, what do we do? Which one do we keep, and which one do we replace with midpoint? And how do we know? So in this column, our lower bound always needs to be greater than 0. Our upper bound always needs to be less than 0. Okay, and that's the function evaluated at our upper bound. Okay, so it's not the bounds themselves, it's the function evaluated at the bound. So we got a positive value. It's small, but we got a positive value, 0.03. Okay, and because it's positive, then we want to replace the lower bound, okay, because this is greater than 0. Okay. So we take our midpoint value, 4.215, and that's our new lower bound. And then our upper bound, which needs to be negative when evaluated in the function, this stays as 4.23. So as we're looking at our function itself, here was our original bracket. And then, okay, here's our original bracket. And we said roughly, so it's 4.20, and here's a 4.23. And then our midpoint, it looks like I didn't draw this very well. It looks like our midpoint gave us a positive value. Let's see if I can draw this a different way here. A little more accurate. There we go. So this was our low bound, 4.20, 4.23. And then when we found the midpoint, when we evaluated that, that was positive. And so we replaced our midpoint here, 4.125 and 4.23. Okay. Right, so we're going to continue doing this where we calculate our midpoint, and I get 4.2225. And then when we evaluate the function at this midpoint, then we get 0.012232. Okay. And so now we would compare 0.012232 to our error tolerance. And then we haven't met that yet. So now for iteration 3, we have 4.2225. Okay, and we're taking this here, similar to how we did here, and we're keeping our 4.23 because when we evaluate this, this is a positive value. We need to keep our lower bounds giving us positive values. And then we'll continue with the calculations. We'll do our midpoint calculation. And then we get 4.2263, which then gives us our approximate root being 0.00477722. Okay, we haven't hit it yet. Okay, we'll go to the next iteration. And in this iteration, our function is still positive. We haven't hit a negative number yet. And so we'll take our 4.2263, replace our lower bound with this value, so 4.2263, keeping our upper bound as 4.23, and then our midpoint between those two is 4.2282, and then evaluating 4.2282 in our function, we get 0.0014749. Okay, which when rounding, if we're only taking our first 3 decimal places, we would then stop. We'd say, okay, we've hit that. And so then our root, according to our criteria here, is 4.2282. And previously, when we've looked for this root, let's change this to our 4th bracket. Let's find out what. This is our answer when using F0. F0 gives us 4.2291. Okay, so if we take this another step, we would actually get 4.2291. Okay, so if our tolerance, if we do one more iteration, so our 5th iteration, okay, we would get below this tolerance, one more step below the tolerance. We would actually get below 0.0001, and then that would give us 4.2291. Okay, which is what F0 came up with. Okay. So what F0 is doing, just to decompose this black box a little bit, is in the F0, when you give it a lower bound and an upper bound, okay, which is a bracket, 4.20 and 4.23, is it's using some form of this bisection method, okay, to hone in on the root itself. Okay. All right, give me a thumbs up if you were following me there. Okay. And so as a quick recap, okay, before you get into this yourself, each time you start with an upper bound and a lower bound. Upper bound was 4.23, lower bound is 4.20. You're then going to calculate a midpoint. okay, based on this. Your midpoint is your approximation of the root, okay? And if you're happy with that particular tolerance or in iterations, and we're going to be working in iterations today. We're not going to be using error tolerances in your function, but that's your root approximation, okay? You then change your bounds, okay? Here was our wide bound. We're going to get a smaller bound that still encompasses the root. That's the goal, is to always encompass the root. And then work through these calculations left to right, okay? And to do that, we're always taking our midpoint and we're going to be replacing the midpoint value with either the lower bound or the upper bound. Okay. Now in this example, we never had where we needed to replace the upper bound. Okay, and we would replace the upper bound if, when evaluating our approximate, our root approximation, when evaluating it, we would have gotten a negative number here. We would have put our midpoint into the column that needed to be negative, into the column in which the function, when evaluated at that midpoint, needed to be negative, or at that root approximation. Okay. So I have this or on Canvas, there's a bisection iterations starter code. So this is the function for bisection. And you can see here that, oh, this is poorly named. So this should be the bisection iterations is the name of it. And so bisections iterations, it's the bisection method applied to a user specified bracket for a set number of iterations. Okay. And so from this, you're going to get a final root approximation of the root, and then also the true absolute error. And so what you're giving it as your inputs are going to be the function handle. So what function are you actually evaluating? Here in our class example, our function is our sine 10x plus cosine 3x. And then you're going to give it the bracket. So that's where you can choose your own bracket by visually inspecting, or as we've done before, by using the incremental search, okay, we get all these different brackets. So you can choose those brackets, you can work your way through them. And then also, the last thing will be to specify the number of iterations that you want it to go through. Okay. Now you saw here in this example, we converged pretty quickly. Okay. Like we did 4 iterations by hand as we're working through this. A 5th iteration would get us the root with a really, really small error. And so that was a good approximation. And so this isn't one where you need to do a lot of iterations. Most of the time, I think like 5 to 10 is good. And so there is a default number of iterations so 10 iterations if you don't specify the iterations. And for that, we're using our in-argin function to determine that. Actually, this needs to be less than 3. Correct that line. So on line 26, in-argin, if it's less than 3, then it goes with a specific number of iterations. You give it the bracket, you give it the number of iterations, and it's going to give you the root approximation. And then also it's going to give you the true absolute error. Okay, and that's an important one because here we know that when evaluating our error, okay, we want to know how close are we when we evaluate our function, how close to 0 we are. So this is one of the problems where we know the answer, or at least we know when we get a root that plugging it into the function we should get a 0, okay, or something very close to 0. And so then down here, as you scroll down, the pseudocode has been placed in here for you. The first step being to extract the lower and upper bounds out of the bracket from the input. And this is attempting to mirror the F0 function, where the bracket itself, the bracket is a one-dimensional array in which you have a lower bound, upper bound that defines the interval. So take out the lower bound, upper bound, and then in this section here, you're going to apply the bisection method for the specified number of iterations. So if it's 10, if it's 15, if it's 27, you're going to go 1 through that number of iterations. Okay, and just like what we did by hand, you'll define the midpoint between the lower bound and upper bound, and then you're going to replace the midpoint using your sign change test. And that's what you're going to do every time. At the end, after you kick out of the loop, then you're going to set the root approximation as the midpoint between your final lower bound and upper bound, and then calculate that true absolute value, and then you're done. That is the bisection method. Okay. All right, so if you follow those parts, okay, and when keeping this half of the bracket, this part here, you're applying that sign, you're applying that sign change test and making that replacement. Okay, sound good? The practice problems are going to be the same that you had from last Friday. Okay, so we can just keep the same problems, and then now you're using your own method instead of calling F0. You don't have to call F0 any longer. Okay, you'll be able to call the incremental search that we did last time, pull out the brackets that you want, and then put them into your own function, which will be the bisection iterations, okay, and come up with your own roots. So do those same two problems, okay, but now using your own bisection function. All right, so that's your assignment. First step is to complete the bisection function. All right, what questions you got on this? Okay, the best way to do this is going to jump in and just do it. Okay, so give me a thumbs up if you were just completely with me. I think Rory is. Colton. Okay. Great. Give me the party if you're just completely gone. Okay, nobody's partying. I don't know what the other symbol is. Give me a thumbs up if you're kind of in the middle. I'll interpret that as a, okay, it's in the end stormy. Okay, well, we got about 10 minutes left. Okay, so just jump in here and get started. And then definitely, you know, make it to office hours, post questions on the board, use this last little bit. I can open up some chat rooms or the breakout rooms as well for everyone else to be able to ask questions. Okay, and I'll be in the main one, all right? Okay, so you've got the help that you need definitely in the last 10, next 20 minutes that we got, okay? 10 minutes, and I can stay later for another 10 minutes to make sure you're on the right track. Okay. Oh, I got something in the chat. Shaky thumb. Okay. Thanks, Rory.